In our ongoing desire to comprehend a vast and mysterious universe, seeing is not just believing, seeing is everything. While we experience life on Earth using all 5 of our senses, in space, virtually everything we know about the universe comes to us through our ability to see. We gather up the light of the stars and galaxies with our telescopes, and by analyzing that light in a multitude of ways, we gradually unlock the secrets of the cosmos. The invention of the telescope changed our understanding of the universe forever, because it allowed the human eye to overcome a natural barrier and see objects that are much fainter and farther away than we would otherwise see. But there's also another barrier that limits what we can perceive when we look out into space. A barrier that can be overcome if we can learn how to see the universe through very different eyes. That second barrier exists because what we experience as light is really a wave of energy. And whether we can see it or not depends on the length of that wave. The human eye can only perceive light waves that range from about 39 to 75 millionths of a centimeter long. That narrow range, known as the visible spectrum, includes all the colors of the rainbow. But where the eye stops, the spectrum of electromagnetic waves, of which light is just one small part, continues. Now, the opening up of that spectrum at many other wavelengths has given astronomers a cosmic rainbow of new possibilities to explore. It began with radio waves. For decades after radio was invented, no one thought it would be possible to receive radio waves from space. Then, in 1931, an American engineer proved that idea wrong. Carl Jansky was working for Bell Telephone Laboratories, trying to identify natural sources of radio interference that might affect transatlantic communications. With a special receiver set up in a New Jersey field, Jansky found a mysterious hiss coming from the sky. Jansky discovered the radio hiss was always strongest when the Milky Way, especially the bright central region of our galaxy, was above the horizon. Something toward the center of our galaxy was producing radio waves. And there were other sources too. An entire radio universe just waiting to be explored. But what kind of universe would the new technology reveal? Looking at the sky through radio eyes, our entire Milky Way shines with the cool glow of hydrogen gas. Even parts of the galaxy that are blocked from our view by thick clouds of interstellar dust can be mapped in this way. Astronomers have used this convenient fact to uncover the spiral structure of the Milky Way. And radio waves can also help reveal more energetic phenomena. A supernova, the explosive death of a massive star, and one of the most spectacular sights in the universe. For centuries after the event, a bubble of energized atoms expands outward, the far-flung remains of the obliterated star. As the supernova bubble crashes into the surrounding interstellar gas, it gives off radio waves, creating what looks like a bright wreath of radio energy. A black hole is formed when matter is squeezed to infinite density, creating a bottomless pit in space. Once inside, not even light can escape the black hole's irresistible pull. On the way in, gas and debris swirl ever closer to the edge of the black hole. Some of this gas manages to narrowly escape and instead feeds massive high-speed jets of electrically charged particles, which fire outward along the black hole's axis of rotation and become strong emitters of radio energy. Today, astronomers know the radio waves emanating from the center of our galaxy, the same signal Carl Jansky first discovered, come from a giant black hole as large as a solar system. And the Milky Way is not alone. Thanks to radio telescopes, it's now clear that most galaxies contain monster black holes, sometimes with active jets, which are among the strongest sources in the radio sky. Seeing the universe through radio eyes has given us a new perspective, allowing astronomers to discover and study phenomena that were once completely unknown. But radio is just the beginning. There are many other ways to see the universe, especially when we leave Earth behind and begin to observe with new eyes in space. The universe that is most familiar to the eye is the universe revealed by light. As stars and galaxies shine across the vast reaches of space, their subtle colors carry important clues about temperature, chemical composition, and distance. But all the colors of light we can see are just small parts of a much larger spectrum that stretches out well beyond the range of human vision, from very long to very short wavelengths. At wavelengths shorter than the human eye can see, light transitions into other forms of energy that can only be detected with special sensors. And because it takes a lot of energy to produce them, these shorter wavelengths, like ultraviolet, X-rays, gamma rays, are ideal for studying some of the most energetic and most violent phenomena in nature. The catch is that Earth's atmosphere blocks most high-energy forms of radiation. That's good news for life on Earth's surface, which depends on the atmosphere like a protective blanket. But it also means astronomers need to get their telescopes off the ground if they want to explore the high-energy universe. The Hubble Space Telescope makes an ideal starting point. Its cameras see what our own eyes see. But by using special filters, astronomers can also zero in on the hotter, ultraviolet part of the spectrum. By showing only the very hottest stars, Hubble gives astronomers a chance to peer deep into a galaxy's core. Another telescope, the Galaxy Evolution Explorer, or GALEX, is dedicated to looking for sources that shine bright in ultraviolet light. These are the most energetic and short-lived stars we know, and astronomers believe they may hold clues to how the galaxies formed and evolved. That's because the hottest stars we see today may resemble the very first stars that formed when the universe was just a small fraction of its current age. When those stars died, their cores collapsed to form black holes. And some theories suggest the black holes merged to form even larger black holes like those we see at the centers of galaxies today. Galax has also found other ways to bring hidden details about the stars to light. For example, the aging and bloated star known as Mira is too red and too cool to be observed in the ultraviolet. But Galax has found that Mira is generating a wind of high-speed particles, which smash into the surrounding interstellar gas, creating a glowing tail that reveals the star's movements for the past 30,000 years. Leaving the ultraviolet behind, the Chandra X-ray Observatory is our guide to an even higher temperature X-ray universe. To collect X-rays, Chandra uses a series of 4 nested cylinders coated with iridium to reflect and direct the X-rays into a sensitive detector. Only objects with temperatures of millions of degrees are able to produce X-rays through heat. Here, a supernova that was witnessed by the astronomer Tycho in 1572 appears like a frozen fireworks display when seen in X-rays. One of the most spectacular sights in the X-ray universe is this stunning panorama from Chandra, showing the region near the center of our Milky Way galaxy. This area is hidden from optical telescopes by dense clouds of interstellar dust. But X-rays, which pass right through the dust, unveil a chaotic spacescape full of churning hot gas and bright specks that could signify where neutron stars and black holes are devouring companion stars. At the very heart of this fascinating region is a bright cloud of gas surrounding what is thought to be the location of the Milky Way's giant central black hole. When combined with a view in infrared light, Chandra's X-ray image is our most revealing glimpse yet of the most extreme location in our galaxy. Looking beyond X-rays, astronomers have also begun to explore the universe at even shorter wavelengths and higher energies. NASA's orbiting Fermi telescope is designed to detect gamma rays. Fermi registers their arrival as they rip through canisters filled with metal plates and split into pairs of matter and antimatter particles. This design allows Fermi to deduce the energy and incoming direction of the gamma rays. One of its most surprising results has been the discovery of 2 giant bubbles of energetic particles emanating outward from the center of our galaxy. The cause of these bubbles, each 25,000 light-years tall, remains unknown. They could be linked to outbursts from the Milky Way's giant black hole. Even more perplexing has been the mystery of gamma-ray bursts, vast explosions that appear all over the sky at great distances, far from our own galaxy. Astronomers believe they may mark the births of black holes from the collapse of massive stars. Perhaps only the Big Bang itself can top an event as powerful as a black hole's birth. But to look for evidence of the Big Bang, astronomers must change perspective yet again and see the universe in a different light. The more we can expand our vision beyond what the eye can see, the more we can learn about the universe. Even in the narrow range of light that the human eye responds to, small differences in color can yield great storehouses of information. Here, with this magnificent view of the Whirlpool Galaxy, over 30 million light-years from Earth, the Hubble Space Telescope plays witness to a great cosmic cycle. The giant spiral waves sweeping through the disk of the galaxy show where vast clouds of hydrogen gas, triggered by gravity, are collapsing to form new stars. The stars light up the gas, which gives off a pink light. In comparison, stars are not forming near the galaxy's central region. There, a population of middle-aged stars gives off a cooler, yellower light. But now, as seen through an infrared camera on the Hubble, we find the galaxy is threaded through with glowing wisps of interstellar dust. The particles that make up the dust are tiny, like smoke. But collectively, and through infrared eyes, they reveal what is going on below the threshold of human vision. Infrared telescopes offer astronomers a way to probe the cool universe at wavelengths longer than the human eye can see. Since the atmosphere blocks most wavelengths of infrared, the telescopes that are best able to exploit this part of the spectrum are in space. The Spitzer Space Telescope is sensitive to the infrared light that is nearest to visible light. With the Spitzer, many celestial objects look familiar, but also just a bit different. Here, the North American Nebula gets its name from bright and dark clouds of gas and dust that vaguely resemble the familiar outline of the continent, complete with the Gulf of Mexico. But using Spitzer's infrared vision, the dark regions suddenly light up, revealing the structure of the dust clouds. Pushing farther into the infrared universe is the Herschel Space Observatory, currently the world's largest orbiting telescope. Herschel looks at longer wavelengths than Spitzer, so it sees even cooler objects. Its specialty is peering into dark, dust-shrouded clouds to see the embryos of newly formed stars. Herschel has shown that even within the coolest, darkest clouds of our galaxy, matter is in motion, like a vast cloud of billowing smoke. Herschel has also cast its gaze beyond the Milky Way to our nearest galactic neighbor, the Andromeda Galaxy. In this view, we see Andromeda first through visible light, with its bright stars and dark lanes of dust. But with Herschel, the stars fade to black, and the dark dust shines like brilliant ribbons. Infrared telescopes are beginning to probe the most distant corners of the expanding universe, where light from rapidly receding galaxies is shifted to longer and longer wavelengths. In the future, infrared telescopes will be crucial as astronomers continue to peer farther and deeper in search of the very first galaxies and the first stars. But even farther down the spectrum, where infrared light transitions into radio waves, astronomers have found a signal that announces the beginning of the universe itself. That signal, which comes to us from every direction in space, first showed up by accident in a horn-shaped antenna operated by Bell Labs in New Jersey. Two researchers, Arno Penzias and Robert Wilson, made the discovery in the mid-1960s, not far from where decades earlier, Carl Jansky first detected radio waves from the Milky Way. Without realizing it, Penzias and Wilson had discovered the cosmic background, light that was emitted by our universe when it was filled with white-hot gas in the aftermath of the Big Bang, nearly 14 billion years ago. Today, satellites are probing the cosmic background and mapping its features in detail. These small variations in wavelength and temperature can reveal volumes of information about the physical properties of the early universe, and may eventually help us understand what caused the Big Bang. "400 years ago, astronomers first turned the telescope to the heavens and discovered there was more to the sky than meets the eye. Now, a host of new eyes in space, as well as radio ears on the ground, have opened up the entire spectrum, giving us a cosmic rainbow of perspectives as we try to piece together how the universe works." It's not just what we see that has changed over the course of this incredible journey, but the idea of seeing itself.